What if everything you've ever touched, every stone, every breath of air was once part of a drifting cloud of cosmic dust, colder than ice and older than Earth itself? Long before planets had names or shapes, before the sun even lit up the sky, the universe was a quiet sea of microscopic particles. And yet, from that emptiness came worlds, mountains, oceans, you. Tonight, we'll journey through that forgotten transformation, how lifeless dust, adrift in silence, slowly became the planets we now call home. If you could float inside that ancient cloud, among particles no wider than a strand of smoke, could you even sense the beginnings of a world forming around you? Imagine a universe without stars, no planets, no moons, no glowing suns to warm the dark, just silence. Endless, stretching silence. That's where our story begins, not with fireworks, but with shadows. Roughly 13.8 billion years ago, the universe was born in a rapid, unimaginable expansion we now call the Big Bang. In its immediate aftermath, it was too hot, too dense, too chaotic for anything as gentle as dust to exist. But as the universe cooled over hundreds of thousands of years, the first atoms, mostly hydrogen and helium, settled into a vast, featureless fog. It took another 100 million years for the first stars to flicker into being, and with them, something quietly extraordinary began. Inside their blazing cores, those stars forged the first heavier elements: carbon, oxygen, iron, silicon. These weren't scattered like seeds. They were trapped inside the hearts of stars, locked away until death set them free. When the most massive of those first stars reached the end of their lives, they collapsed and exploded in colossal supernovae. In their final breaths, they scattered their innards into space, seeding the universe with the raw materials of everything yet to come. What floated outwards was dust, fine, solid grains forged in fire, now drifting cold and alone. These grains weren't like the dust that settles on shelves. They were cosmic relics, tiny, irregular particles of rock, metal, and ice, some smaller than a virus, others no bigger than a grain of salt. Yet in their simplicity, they carried complexity. Some contained crystalline structures, formed at incredible temperatures. Others trapped noble gases or radioactive isotopes, quiet signatures of violent births. Over billions of years, more stars were born and died, repeating the process again and again. Each generation enriched the interstellar medium, the thin gas and dust between stars, layer by layer. Like snow accumulating on a field, this dust collected silently, forming clouds more massive than 1,000,000 suns, though so diffuse they would seem invisible to the naked eye. And within these clouds, colder than any winter night on Earth, something was stirring. When a molecular cloud reaches a certain mass and density, it begins to collapse under its own gravity. Small fluctuations, perhaps triggered by the shock wave of a nearby supernova or the gentle ripple of galactic rotation, can tip the balance. Once collapse begins, regions within the cloud start to concentrate, pulling in more material, growing denser, colder, and darker. At the heart of one such cloud, a faint glow would eventually emerge. The very beginnings of our sun. Around it, a spinning disk of gas and dust formed, shaped by angular momentum and magnetism. Here, in this thin, dusky halo, the raw ingredients of planets began to gather. But this dust, the stardust, was not immediately eager to become anything more. Left alone, dust tends to drift, to collide and bounce, to remain scattered. So what changed? Before we get there, pause for a moment. Consider this: the atoms in your body, your bones, your blood, your breath, very likely formed inside a dying star. You are, quite literally, made of ancient dust. And that dust was once cold, drifting in the dark, waiting to become something. The formation of planets from dust is not a sudden event. It is a patient one. It begins in the quietest corners of the universe, where time moves slowly and forces act with the gentlest persistence. In these cold beginnings, the seeds of worlds are planted, not with noise, but with stillness. As the young sun ignited and cast its first light across the swirling disk, the dance of dust truly began. And in that dance, the first whispers of planets stirred. Let's follow those whispers into the next stage, where dust begins to gather and gravity begins to guide. Picture this: billions of tiny dust grains, each one no larger than a speck of ash, orbiting a young star. They move not in chaos, but in slow spirals, each following an invisible path carved by gravity and motion. This disk, thin and flat like a record, stretches for hundreds of millions of kilometers. It is quiet, cold, and vast. But within it, something is happening, so gradually that if you watched for a million years, you might only see the first signs of change. This is the protoplanetary disk, a fragile nursery of gas and dust encircling a newborn star. And here, in this dim light, gravity begins its slow, deliberate work. At first glance, dust should remain dust. The particles are tiny, and the space between them is immense. Collisions happen, yes, but more often than not, grains simply bounce away from each other. Some even shatter. The odds seem impossibly small. But over time, patterns emerge. Gravity doesn't shout. It whispers. Each dust grain, though small, has mass, and with mass comes gravity. On its own, a single grain exerts a force so weak it's practically non-existent. But when grains clump together, first 2, then 10, then 100, their combined pull becomes noticeable. A gentle attraction forms, drawing in other nearby particles. Slowly, a few grains become a cluster, then a pebble, then something more. But gravity is only part of the story. Electrostatic forces, yes, the same kind that makes socks stick together in the dryer, play an unexpected role in these early stages. In the cold vacuum of space, where particles can carry small electrical charges, oppositely charged grains attract. This charge-based clinginess helps dust grains stick when they collide gently. These early, fragile connections are delicate. A fast collision would tear them apart. But in the quiet orbits of the disk, collisions are often slow and soft, more like settling snowflakes than smashing rocks. Over thousands of years, these sticky interactions help dust grow into larger clumps. Millimeter-sized aggregates, often called fluffy particles because of their loosely packed structure. These clumps begin to settle toward the midplane of the disk, where most of the material orbits in a flat, dense layer. Here, the chance of collision increases dramatically. As more particles accumulate in this plane, gravity begins to organize them, not forcefully, not quickly, but with persistent pressure. A denser region pulls more material toward it, which increases its gravity, which pulls even more. A feedback loop begins, slow and inevitable. Over tens of thousands of years, some clumps grow to the size of pebbles, then rocks. Still, the process remains fragile. Collisions at higher speeds can be destructive. Two clumps meeting too quickly might not stick. They might shatter or bounce apart, erasing thousands of years of growth in an instant. This problem, known as the meter-size barrier, presents one of the great puzzles of planet formation. How do objects grow from dust to something large enough that gravity takes over completely? Some scientists believe that gas plays a role here, not just as a passive backdrop, but as an active participant. The gas in the protoplanetary disk isn't still. It flows and churns, shaped by the young star's magnetic field and by temperature differences across the disk. These flows can concentrate dust in certain regions, like eddies in a river catching leaves. In these pockets of higher density, collisions become more frequent and more favorable. There's another player in this quiet dance: turbulence. Though it sounds chaotic, turbulence in the disk may help dust grains concentrate in thin bands or swirling vortices, giving them more chances to collide gently. Imagine tea leaves spinning at the bottom of a cup, slowly gathering at the center. In the disk, these turbulent traps may serve a similar purpose, bringing particles close enough, often enough, to encourage growth. And so, over thousands, millions of years, tiny clumps become larger aggregates. Some grow to the size of boulders. At this stage, gravity becomes stronger. Strong enough not just to attract dust, but to hold on to it. These growing bodies begin to dominate their immediate surroundings, carving out tiny zones of influence in the vastness of the disk. These early planetesimals, still small, still vulnerable, are the first tangible signs that the process is working. That dust, with enough time and guidance, can become worlds. But this stage is not peaceful. As clumps grow, they begin to compete. Some will succeed, many will not. Before we watch these early worlds contend for space and survival, let's pause. In the silence of space, with only the faint hum of starlight, the transformation from dust to rock has already begun. Not with force, not with speed, but with time, gravity, and the quiet pull of inevitability. Imagine floating in the heart of a slow-turning spiral. All around you is dust cold, fine, drifting with the ease of breath. There's no sound, no wind, no ground beneath your feet, only the vast, glowing blur of a young star behind you, and a wide, dark disk of swirling material stretching out in every direction like a forgotten dream. This is the protoplanetary disk in full bloom, a structure born not of chaos, but of balance. Rotation, gravity, and pressure find an uneasy harmony here. It is the cradle of all planets, and yet, to the casual glance, it seems empty, silent, and slow. But look deeper, and you will see a process so patient and perfect it defies the urgency of time. The disk is thin, but wide. Its inner edge might be just a few million kilometers from the young star, blazing hot with temperatures high enough to melt rock. But venture farther out, tens or even hundreds of astronomical units, and the light dims, the gas cools, and ice begins to form on dust grains. The disk is stratified, with different regions offering different environments for the formation of planets. Closer to the star, metals and silicates dominate. Farther out, beyond a boundary called the frost lines, ices can remain solid. This invisible threshold, often just a few astronomical units from the star, marks the point where temperature drops low enough for volatile compounds like water, ammonia, and methane to freeze. Beyond it, planet formation can take a different turn entirely. Here, in the outer disk, where sunlight is little more than a pale suggestion, icy dust grains clump together more easily. The abundance of frozen materials increases the total solid mass available for planet building, allowing larger cores to form. These may one day grow into gas giants. But that comes later. For now, we return to the disk itself. This slow, luminous carousel of matter. It is not smooth. The gas and dust do not spread evenly. Instead, the disk is a patchwork of pressure bumps, density waves, and vortices, subtle structures shaped by gravity, heat, and magnetism. Some of these irregularities arise naturally. Others may be triggered by the earliest growing bodies, clumps of material already large enough to disturb the flow around them. In some regions, turbulence dominates, churning the gas, lifting particles upward, creating gentle collisions and chaotic motion. In other regions, the gas flows more smoothly, allowing dust to settle toward the disk's mid-plane, forming a dense, concentrated layer where collisions become more likely. It is here, in this razor-thin plane, that the seeds of planets gather. The gas itself plays a quiet but crucial role. It drags on the dust grains, slowing their motion, pulling them inward. This inward drift is a problem, especially for particles in the centimeter to meter size range. If they don't grow fast enough, they may spiral into the star and be lost forever. And yet, somehow, some grains overcome this fate. Some grow large enough to resist the drag, to stay in place, to keep collecting more. The disk, vast as it is temporary. Within a few million years, the gas will disperse, blown away by radiation from the star, or accreted into larger bodies. That gives the dust a limited window in which to build planets. And yet, across countless stars and systems, it happens again and again. What guides it? There are no blueprints, no master plans, but there are patterns emerging not from design, but from nature's quiet persistence. The disk isn't a storm, it's a slow tide, a gentle unfolding of the possible. And within it, dust collects, settles, merges. Some clusters remain small, never escaping their fragile state. Others grow large enough to shape the gas around them, creating wakes like boats on a lake. In some regions, resonances form subtle patterns that channel material into orbits where growth becomes easier, and sometimes a large enough object begins to clear a path through the disk. It sweeps up material or pushes it aside, leaving behind a gap faint but widening. A sign that something more than dust is moving through the disk now. Something heavy, something real. As the star matures, the energy it emits increases. Radiation and stellar winds begin to erode the outer edges of the disk. Over time, the gas thins, the dust settles, and the once luminous spiral begins to fade, but not before it leaves behind its legacy. Planets do not form in an instant. They emerge slowly, shaped by their environment. And the protoplanetary disk, though temporary, is the stage upon which every planet's story begins. Now, within this fading disk, the clumps of dust and ice that have survived the early hurdles begin to take on new identities. No longer just aggregates of chance, they become the building blocks of worlds. Next, let's follow them into the stage where size and mass begin to matter, and where the collisions are no longer soft. Drift far enough into the dark corners of the disk, and you'll find silence layered in silence. A hush so deep, it almost feels physical, like velvet pressed against your ears. Here, in the mid-plane of the protoplanetary disk, a quiet struggle is unfolding. Small clumps of dust, some icy, some rocky float, in near weightlessness, slowly approaching each other through gas and gravity. They do not crash, they do not shatter, they touch, and sometimes they stay. This is the strange and delicate heart of planet formation. Not explosions, not heat, just soft collisions like snowflakes landing in slow motion. And from these fragile encounters, worlds begin to grow. At first, it seems impossible. The particles are too small, the force is too weak, the collisions too rare. A grain of dust has no muscles, no tools, no will. It is acted upon, not acting. Yet when two grains touch under just the right conditions, at low relative speed, at the right angle, they may stick. Electrostatic charges, surface irregularities, and even thin films of ice can help them bind. These earliest structures are called aggregates. They are white, porous, and weak. Imagine a dust bunny under a bed, but floating in the void. That's what the first clumps look like. Loose tangles of particles, held together by nothing more than delicate physical chemistry. They are not alone. The disk is full of them, drifting gently through the gas, settling into the mid-plane where the density is highest. And in this gentle region, collision rates rise. Every touch is a possibility. Over thousands of years, these fluffy structures bump into one another, growing in size. Millimeter-sized particles become centimeter-sized clusters. The clusters become decimeter globs. With each stage, gravity strengthens, though still faint. Barely enough to notice. But something else begins to matter now. Drag. Gas in the disk slows down solid particles. Smaller grains, with low mass, are strongly affected. They move with the gas. But as aggregates grow larger, their inertia increases. They begin to decouple from the gas and follow more independent orbits, drifting inward toward the star as they lose angular momentum. This inward migration is fast too fast, some might say. Aggregates about 1 meter in size can spiral into the star in just a few hundred years. It's a problem. Grow too slowly, and you fall inward before reaching planetary size. Grow too quickly, and collisions may destroy you. So, how do some survive? It's here that subtle physics begins to shape destiny. In some regions of the disk, pressure bumps, areas where gas piles up, act as barriers, halting inward drift. Dust collects here, like debris caught in a tide pool. Within these pressure traps, aggregates can grow in relative safety, shielded from both inward drift and violent collisions. At the same time, turbulence within the disk stirs the dust into eddies and swirls. These vortices concentrate particles, giving them more chances to meet and merge. Picture flour slowly stirred in water. It does not dissolve evenly. It clumps, forms clouds, sinks. So too with dust in the void. And as these clusters grow, they begin to compact. The once fluffy structures are compressed by new impacts, squeezed by their own increasing mass. They become denser, stronger. No longer delicate webs of dust, but solid clumps. Still small, still vulnerable, but no longer ephemeral. At around a kilometer in size, something changes. Gravity, once a whisper, begins to speak. These bodies, called planetesimals, now have enough mass to attract other material. Not weakly, but decisively. They begin to pull in smaller particles to sweep their paths clean. Some collide with each other, creating new bodies. Others collide and shatter, spraying fragments back into the disk. The rules shift here. We move from the physics of sticking to the physics of pulling, of attracting, of competing. But even before this transition, one truth remains. The process is slow. You could stand in the same spot for 1,000 years and never witness a collision. And yet, over 1,000,000 years, 1,000 such collisions might take place. Each one, a silent event, a step towards something larger. Even now, as you lie still, imagine one of those particles, formed from a long-dead star, coated in ice, drifting alone, finally brushing against another. A slow tumble, a meeting, a beginning. This is how it always starts. Not with fire, but with quiet contact. And a moment enough of these contacts have built something big enough to matter, gravity takes over in full. Let's now step into that threshold, when small bodies start growing fast and the dust becomes stone. Consider the size of a pebble, something you might hold in your hand, smooth from time, modest in presence. Now imagine that same pebble, not on Earth, but floating in a disk of ancient gas and dust, orbiting a star not yet fully grown. It has no will, no direction, but it drifts slowly, gathering smaller particles in its path. With time, it becomes more than just a pebble. It becomes the seed of a planet. This is the next stage in the formation of worlds, the quiet leap from scattered clumps to solid building blocks, planetesimals. To reach this milestone, a pebble must grow, not just by colliding with other particles, but by surviving the treacherous journey inward, resisting destruction, and reaching a size where gravity becomes its silent protector. And this is not easy. One of the great challenges in this phase is the so-called meter size barrier. As pebbles approach sizes between a few centimeters and a meter, they experience a kind of death zone. These intermediate bodies are too big to stick easily, and yet too small to gravitationally attract new material. Worse still, they face rapid inward drift due to gas drag. Within a few hundred orbits, many spiral inward toward the star and are lost. And yet, not all are lost. Some make it through. How? Modern models suggest that growth may not rely solely on individual collisions. Instead, pebbles may grow by streaming instability, a cooperative process in which dense concentrations of small solids trigger local collapses. In these regions, pebbles cluster together, dragged into knots by their mutual gravity and the flow of gas around them. These knots can collapse into solid planetesimals in a relatively short time. decades or centuries rather than millennia. Imagine it as dust gathering in a rain cloud. At first, particles float freely, but as moisture condenses, droplets form. Then, gravity pulls those droplets together until a raindrop falls. In the disk, the result is not a raindrop, but a rock, tens or even hundreds of kilometers wide. These planetesimals are not formed by fragile sticking, they're forged by collapse. And because of that, they are solid, dense, and capable of surviving the harsh reality of orbital mechanics. Once they appear, everything begins to change. They exert gravity, not much, but enough. They begin to dominate their surroundings, clearing paths through smaller particles. Their gravitational pull can capture pebbles, a process known as pebble accretion. The efficiency of this process depends on location, temperature, and disk structure. But in the right conditions, it can be rapid. A single planetesimal can double in size in just a few thousand years. As these bodies grow, collisions become more energetic. When two planetesimals meet, the outcome depends on their size and speed. Some impacts result in merging, two worlds becoming one. Others end in fragmentation, with debris scattered back into the disk. These fragments may later reassemble or feed other growing bodies. This stage is messy. Planetesimals carve out orbits. Some remain stable. Others are thrown into chaos, ejected, broken, or devoured. The disk, once gentle and uniform, becomes sculpted. Gaps appear. Edges sharpen. The architecture of a planetary system begins to emerge. Not clearly, not fully, but the scaffolding is in place. It's important to understand the scale here. A planetesimal may be only a few dozen kilometers across. It is not yet a planet. It has no atmosphere, no moons. It drifts in silence, cold and alone. And yet, it holds the blueprint of something far larger. On some distant worlds, we can still see the remnants of these early days. On the moon, on asteroids, in comets, they carry the fingerprints of their birth porous interiors, fractured surfaces, odd mixtures of ice and rock. They are the fossils of planet formation, but not all planetesimals remain fossils. Some continue to grow. If they gather enough mass, they begin to attract not just solids, but gas. Their gravity creates envelopes. Heat from impacts and radioactive decay melts their interiors. Differentiation begins. Iron sinks. Silicates rise. Cores form. They become differentiated bodies, miniature planets in their own right. Some may eventually collide with others, growing into embryos, then protoplanets. Others are captured by larger worlds, becoming moons. Still others are flung outward, exiled to the dark edges of the system. But it all begins here, from dust to pebbles, from pebbles to planetesimals, a transition not of sudden leaps, but of quiet persistence, slow growth, a soft but steady accumulation of mass, guided by gravity's invisible hand. Next, we'll witness the next great step, the chaotic ballet of collisions, where planetesimals battle for survival, merging into protoplanets, and setting the stage for true planetary birth. Imagine a sky filled not with stars but with stones, massive bodies miles wide drifting through space in looping, intersecting paths. Some spin slowly like forgotten clocks. Others tumble violently, the scars of ancient impacts visible in every crater. The silence is deceptive because this is a time of violence, hidden beneath the slow veil of cosmic time. This is the age of collisions. The planetesimals, having formed from dust and pebble, now exist by the thousands, perhaps millions, within the protoplanetary disk. But this abundance cannot last. There is not enough space, not enough material, and certainly not enough time for all of them to survive. So the disk, once a calm cradle, becomes a proving ground. The gravity of the young star still dominates, pulling everybody into orbit. But these orbits are not perfectly circular. They are eccentric, tilted, unstable. Over time, planetesimals are nudged by one another's gravity, pushed into new paths, some crossing, some colliding. Each encounter, a moment of chance, sometimes gentle, often catastrophic. When two planetesimals collide, one of three things happens. They may graze and glance off, losing only dust. They may shatter, sending fragments spiraling in all directions. Or, if the conditions are just right, they may merge, becoming something larger. It is this last possibility that leads us onward. Merging planetesimals begin to form protoplanets, the first bodies large enough to resemble planets in mass and structure. These are worlds in progress, tens to hundreds of kilometers in size at first, growing to thousands. Their gravity is now strong enough to dominate their local neighborhood in the disk. They become gravitational centers, drawing in smaller planetesimals, sweeping up dust, and competing with other protoplanets for material. The process is sometimes called oligarchic growth. In this stage, a few large bodies, the oligarchs, begin to outpace the rest. They grow faster, attract more mass, and exert stronger influence. Around each oligarch, a feeding zone emerges. Material within this zone either accretes onto the protoplanet or is flung away. But this growth comes with a cost. As protoplanets grow, their gravitational fields disturb the disk around them. They increase the eccentricity of nearby objects, stirring the region into chaos. Collisions become more energetic. Destruction becomes more common than creation. This is a dangerous time. One body might spend millions of years growing, only to be shattered by a single collision. Another might survive long enough to clear its orbit and begin gathering a thin atmosphere. Still another might be flung from the system entirely, becoming a rogue world, drifting between stars. These interactions are not neat or predictable. They play out over millions of years. Some protoplanets spiral inward, falling into the star. Others migrate outward, riding the waves of disk instability. A few find stable orbits and remain, quietly growing, cooling, maturing. It is during this time that the final architecture of a planetary system begins to take shape. In the inner regions of the disk, where temperatures are high and only rock and metal remain solid, smaller, terrestrial planets begin to form. They grow more slowly, but more steadily, forming tight, rocky worlds like Earth or Mars. Farther out, beyond the frost line, protoplanets are larger, colder, and richer in ices. Their cores may grow massive enough to attract gas, becoming gas giants like Jupiter or Saturn. Or they may remain icy and small, becoming ice giants or frozen dwarf planets. Each collision reshapes not just the object, but its future, Some collisions are glancing, stripping away crusts and exposing molten cores. Others are head-on, merging two bodies into one and releasing enough energy to melt rock and vaporize metal. Still others scatter debris into orbit, some of which may later form moons. It is believed that our own moon formed from such an impact, a Mars-sized body colliding with the early Earth, flinging molten rock into space, which later coalesced into the companion we know today. The process is long, messy, and deeply random. There is no fixed path, no perfect formula. Every solar system that forms follows the same broad rules, but the outcomes vary wildly. Some end with tightly packed rocky worlds, others with giant planets flung into eccentric orbits. Some systems are serene, others are wreckage, but always, the story is one of persistence. Planets are not born in peace. They are forged in collision, shaped by destruction as much as by growth. And when the disk has finally thinned, when the gas is gone, the dust has settled, and only the largest survivors remain, what's left is a planetary system, a family of worlds, each carrying within it the memory of every collision, every impact, every quiet merging of dust that came before. Next, we'll explore what happens when gravity grows strong enough to capture not just rock and dust, but gas itself, forming the giants of the outer worlds. Far beyond the warm glow of the young star, past the frost line where water and other volatiles freeze into solid ice, a different world of planet formation unfolds. Here, the cold reigns, and the raw materials for building something vast and mysterious lie in abundance. This is the domain where gas giants begin to take shape. The early protoplanets formed beyond this frost line are not mere rocks. They are icy cores, sometimes tens of times the mass of Earth, made of rock and frozen compounds. These massive cores, forged through the slow gathering of planetesimals and pebbles, possess a gravity strong enough to pull in the thick hydrogen and helium gas that dominates the protoplanetary disk. Unlike their rocky siblings closer to the star, these cores don't simply stop at solid matter. Once a core reaches a critical mass, roughly 10 times Earth's mass, its gravity can overcome the pressure of the surrounding gas. It begins to accumulate a dense atmosphere, a thick envelope of hydrogen and helium drawn directly from the nebula. This process, known as runaway gas accretion, marks a rapid transformation. The protoplanet swells, growing not just by solids, but by vast amounts of gas. In a few 100,000 years, it can increase its size many times over, forming a massive, mostly gaseous world. This is how giants like Jupiter and Saturn come into existence. Yet, the environment is delicate. The gas in the protoplanetary disk is not infinite. Stellar radiation, stellar winds, and disk turbulence gradually disperse it over a few million years. If the core grows too slowly, the gas may vanish before the planet can capture a thick atmosphere. Conversely, if the core forms quickly, it can amass a gas giant before the disk fades. The gas giant's birth is marked by both patience and urgency. As the envelope grows, it heats up from compression and energy released by infalling material. The core may remain solid, but it's cloaked beneath thousands of kilometers of swirling hot gas. Inside, pressure and temperature rise dramatically, driving complex chemical reactions and creating layered structures. The gas giants don't just sit still. Their gravity affects the disk, carving gaps and shaping flows. These gaps can influence the orbits of nearby forming planets, potentially pushing them inward or outward. The giants themselves may migrate, sometimes spiraling closer to the star or farther out. Their moons begin to form in miniature disks of gas and dust around them, small worlds born in the shadow of giants. Beyond the giants lies a further frontier. Ice giants like Uranus and Neptune form similarly, but with less gas. Their cores may be similar in size, but they capture smaller gaseous envelopes, resulting in worlds dominated by ices and thick atmospheres of methane and ammonia. Farther still, smaller icy bodies linger, remnants of the early disk, frozen in time. The birth of gas giants is a story of extremes, vast masses, powerful gravity, and the gentle limits of cosmic time. It is a quiet revolution that transforms a simple disk of dust and gas into a complex system of worlds, each with its own path, each with its own story. As the gas disperses and the dust settles, the stage is set for the final acts of planetary evolution. Collisions, migrations, and the quiet settling of a new solar system. Next, we will explore these last chapters, the final shaping of planets, their migration, and how the quiet dust of a disk becomes the vibrant worlds we know. Even as the gas giants grow massive and the dust settles, the story of planet formation is far from over. The quiet disk that once nurtured dust and pebbles is thinning, but the young planets within it continue to move, shift, and evolve. This is the final, slow dance, a process of migration, collision, and subtle sculpting that will define the ultimate architecture of a planetary system. In the early days, planets form roughly where their building blocks were most abundant, but orbits are not fixed. The gravitational pull between planets and the remaining disk of gas and dust causes shifts, sometimes slight, sometimes dramatic. This movement is called planetary migration. Gas still swirling in the disk exerts forces on planets, creating waves and wakes much like a boat moving through water. These interactions can cause planets to spiral inward toward the star or outward to colder regions. The direction and speed depend on many factors: planet size, disk density, temperature, and more. Migration can bring planets into resonant orbits, where their periods become linked in precise ratios, like a cosmic rhythm. It can cause collisions or near misses, shaking up the stability of the system. Smaller planets are often more vulnerable. They may be swallowed by the star or ejected into deep space, becoming rogue planets wandering the galaxy. Larger planets can shepherd debris, clearing gaps and shaping belts of asteroids and comets. Collisions continue during this phase, but at a slower, gentler pace. Protoplanets that avoided destruction in the earlier chaos may now collide and merge, growing into fully fledged planets. These impacts release energy, melting interiors, creating magma oceans, and sometimes stripping atmospheres. The young Earth experienced such impacts. One of the most significant thought to be the giant collision that formed our moon. These final, violent acts were critical in defining the planet's composition, rotation, and habitability. Meanwhile, in the outer system, icy bodies settle into stable orbits, forming belts and clouds of comets and asteroids, the leftovers of formation, Waiting silently in the dark, over millions of years, the gas dissipates, collisions wane, and orbits stabilize. The system cools. Planets develop atmospheres, weather, and sometimes the conditions for life. What began as dust, almost imperceptible in the vastness of space, has grown into a complex system, a solar family with worlds unique and varied. This slow, quiet process is ongoing everywhere in the cosmos. Around other stars, in distant clouds, new disks are forming. New planets are slowly emerging, and though we cannot see these first steps with our own eyes, they are written in the rocks beneath our feet, in the patterns of the night sky, and in the gentle turning of our world. The story of how planets form from dust is not a tale of sudden fireworks, but of gradual wonder, where tiny particles meet, stick, grow, and change under the invisible hand of gravity, patience, and time. Thank you for journeying through this quiet, cosmic dance. As you settle into stillness, imagine the slow, patient dance of countless specks of dust drifting through the vast, silent expanse of space. Each tiny grain touched by unseen forces, gently coming together over ages beyond counting, building, shaping, becoming. The quiet birth of worlds, unfolding softly like a whispered lullaby from the cosmos itself. Breathe deeply and feel the calm of this ancient process, the steady rhythm of time and gravity weaving the fabric of planets, of moons, of life itself. Let your mind drift on this gentle current, carried away by the quiet wonder of creation. Allow the stars to watch over you as the universe slowly spins its endless tale. And in that vast, peaceful space, may your thoughts soften, your breathing slow, and your body rest deeply and completely. Good night.